Here's an effect that you've all observed before while watching a movie in which the wheels of a car are spinning or the blades of a propeller are rotating. And as the rotation increases, you can sometimes observe the optical illusion of the rotating object standing still and jittering around, and sometimes even reverse its direction. This effect is commonly referred to as the Wagon effect, and it exists because any analog or digital video that we are used to in the conventional form is not continuous by any means. It's a series of still pictures projected onto a screen in rapid succession. This video was produced and is hopefully being streamed at 24 frames per second. 24 still images distributed within a span of 1 second. What happens when we try to capture something fast? You get a lot of visual artifacts, and the Wagon effect is one of them. It happens when the successive frames of the images coincide with previous frames' position after the rotation. The rotational speed required to achieve a standstill illusion depends on the general shape of the wheel and the number of spokes it has. But simplifying the wheel to just one spoke, we can see that when the rotation of the body is less than 12 rotations per second, we can generally make out the direction of rotation based on these individual frames. At exactly 12 rotations per second, not much can be determined, and as you increase the rotational speed beyond 12 rotations per second, we can see that the individual frames tell a different story. When given this set of still images, rendered at the right speed, there is only one possible conclusion we can draw, that the rotation is in the opposite direction. The still frames are essentially portraying a false perception of direction, because we broke the boundary above which we don't have enough frames to accurately depict the true picture. And this phenomenon is called temporal aliasing. This seems awfully familiar to our earlier discussion on aliasing within audio signals. We can almost substitute the same terminology here and say that the video is sampled at 24 frames per second, and that 12 frames is the Nyquist limit we need to abide by. In fact, aliasing doesn't just occur in audio and video signals, it occurs in any form of signal which is discrete and is constrained by some sampling parameters. Let's get into temporal aliasing in audio signals. Before we delve into illustrating how a low sampling rate coupled with high frequencies can cause aliasing, we'll first listen to what aliasing sounds like. This is generally harder than it seems, because modern signal paths are really good at eliminating aliasing. When an analog signal passes through an analog to digital converter, it filters out all frequencies above the Nyquist rate. And when a sampled digital signal passes through a digital to analog converter, essentially the same process of filtering occurs. We can't bypass these steps to force aliasing because they're baked into the analog circuitry. Our only hope is to introduce high frequencies within the signal in the digital domain. Even then, modern commercial applications and plugins like pitch shifters and compressors and ring modulators, which actually create higher frequencies within our digital audio signals, are aware that aliasing is a possibility when the signal is processed, and they account for it by internally oversampling the signal. Sometimes this mechanism is transparent and you wouldn't even know that it's happening. And sometimes they give you the option to choose the degree of oversampling. As a producer of music, then, you're well insulated from the effects of aliasing in most cases. But as a developer, battling the effects of aliasing could be daunting. The aim of this video is to give you enough clarity and understanding of aliasing, irrespective of what you plan to do, and hopefully you can continue the investigation further depending on your needs and use cases. We're back in Audacity with a project sampling rate of 8 kHz. If you can recollect from the video on the sampling theorem, we can't generate a sinusoidal tone higher than the Nyquist frequency of 4 kHz. Today we'll bypass this rule and generate higher frequencies. One way to do this is by programmatically telling Audacity to create a tone for you. We can leverage a high-level programming language, coincidentally called Nyquist, to write a little snippet of code. The language is built tightly into Audacity as it offers a prompt where you can run and test pieces of code without the need for an external compiler or interpreter. The Nyquist programming language is huge, with a lot of neat functionality, which you can essentially use for sound synthesis, writing software instruments and effects, and even building plugins compatible with Audacity. But today we're going to look at something simple. Let's go to Tracks add a new track, and select a mono track. Let's select a good bit of the track and head over to Effect and select Nyquist Prompt. Over here, I'll type in return HZOSC, open parenthesis, 7000, close parenthesis. HZOSC, or HZOSC, is a function which stands for Hertz oscillator, and the first parameter that it accepts is the frequency in Hertz. So I've plugged in 7000 as the frequency. By default, the function will return a sine tone with a frequency of 7 kHz with a maximum amplitude set to 1. And I'm returning control and the output back to Audacity by using the return keyword. If I press OK, it will generate the tone within our selection. Right, that doesn't sound like 7 kHz. If we zoom in to examine the waveform, it looks decently well sampled. If we do spectrum analysis of the tone in Sonic Visualizer, we see that it's a very precise 1 kHz representation. Our original 7 kHz tone has been transformed into a 1 kHz tone when our sampling rate was set to 8 kHz. I'll repeat this entire process with an input of 6 kHz. This time we get a higher frequency representation of 2 kHz. You can almost see a pattern here, but let's put a picture to this pattern. I want to generate a sinusoidal sweep from 0 Hz all the way up to the sampling rate of 8 kHz. We'll go back to the Nyquist prompt and we'll change the command slightly to achieve the sweep. We'll include a ramp function inside our HZOSC function. The ramp function creates a linear control signal from 0 to 1 over the duration of 1 second. But since we're using the Nyquist prompt, the duration is relative to our selection. We are then multiplying the control signal with a scalar value of 8000. This creates a linear ramped signal from 0 till 8000 over the duration of our selection. And this control signal is passed into the frequency parameter of the Hertz oscillator. This is the aliasing pattern we see. All the frequencies above the Nyquist frequency of 4 kHz are folded back onto the original spectrum. It doesn't just stop there though. The folding happens constantly at the sampling boundaries as the input signal frequency increases. This is what a 16 kHz sine sweep would look like when sampled at 8 kHz. The sampled signal is folded 3 times over. We can plot a graph of the frequency over time for the original input signal and the raw sampled output signal. Let's draw a line cutting through a single frequency we want to observe. Let's say 1 kHz. We can see that 1 kHz is a recurring frequency within the sampled signal, but only appears once in the original input signal. Input frequencies that are inferred as 1 kHz are 7 kHz, 9, 15, 17 kHz, and so on. It keeps going. You can find out all the possible aliases of a given frequency by this formula, where f of s is the sampling frequency, f is our given frequency, and n is any whole number above 0. A profound implication that can be stated from all this is that there are an infinite number of aliases for every sampled frequency. Even more profound is the fact that any sine wave is indistinguishable from an infinite number of other sine waves after sampling. And this is where the problem lies. Let's say that now we regret not having had a filter to cut off frequencies above the Nyquist, and we want to get rid of the folding effect that has been plaguing our output sampled signal. How do we do this? We can't. Once an aliased frequency enters the sampled signal, it is indistinguishable from all the other valid frequencies. There's no telling them apart. Let's illustrate the sampling process. I'll fix the sampling interval to be constant, and I'll vary the frequency alone. At a low enough frequency, the sampling process is quite nicely churning out data points that abide by the sampling theorem. As the frequency of the signal increases, there are fewer data points representing a single cycle. As long as the frequency is below the Nyquist, meaning that as long as there are at least 2 data points representing a cycle, we're good. But as the frequency increases beyond the Nyquist, there are fewer than 2 data points representing a single cycle of the signal, and the sampled signal has now lost the ability to represent that frequency. Both the data points left behind by the input signal still exist, however, and since there is always a single band-limited signal that can pass through all these data points, the alias of the original frequency is born. Technically, the pattern of data points formed by this aliased signal and this legitimate signal are both the same and produce the same output signal. This is the reason why both the frequencies are indistinguishable once sampled. And all of this is reason enough to be putting so much emphasis on the input low-pass filtering stage in the ADC, from which point on will be referred to as the anti-aliasing filter. A proper anti-aliasing filter would never allow frequencies higher than the Nyquist to enter into the sampled signal. The same applies to software algorithms and components. The reason we were able to achieve aliasing is because we forced it. In the prompt, what you write is what you get. We scripted high-frequency sinusoids without referring to filtering, and that's what we got. The effects of aliasing will never be as pronounced as how we portrayed it in the Audacity demo. Aliasing usually manifests itself as an unintended consequence of working in the digital domain, either during sound synthesis or signal processing. So let's look at a real-world example. We'll use square waves this time around. We'll go to Audacity, select 44.1 kHz as our sample rate, go to Generate, Tone, and select Square as our waveform, and dial in 1370 Hz. That sounds pretty awful. It's absolutely inharmonic. Why does this happen? Any waveform can be produced by adding together a number of sine waves. A square wave is produced by adding a fundamental sine tone along with all its odd harmonic partials. The harmonic series will be discussed in further detail later, but all you need to know now is that the fundamental frequency is our starting base frequency, and a harmonic partial is an integer multiple of the fundamental frequency. For square waves, we select only the odd-numbered harmonic partials, and these partials are scaled down by a factor of their index. If you add enough partials together, you get a close approximation of the square wave, but you'll never be able to achieve the perfect square wave. That's because you'd need an infinite number of partials and an infinite bandwidth to represent them. But this is the digital domain after all, and you can essentially do anything you want. Audacity probably implements wavetable synthesis to produce a square wave. In this case, the data points for a perfect square wave are already stored in a tabular form, and this table is scanned at the rate of the desired frequency. This will give us a near perfect square wave, but along with it comes a ton of high frequency partials that will be aliased back into the original signal, because their frequencies are above the Nyquist. If you look at the spectral analysis of the 1.37 kHz square wave we just produced, you can find about 8 of the highest intensity partials are frequencies that should genuinely be in our spectrum. And all the rest of the lines are just low intensity, high frequency partials that have been folded back into the signal over and over again several times as they all exceed the Nyquist frequency of 22.05 kHz. The worst part about aliasing is that the partials lose their harmonic relationship with the fundamental as soon as they are folded back into the signal. And this results in a sound that is inharmonic and atonal. Aliasing is also irreversible and near impossible to get rid of at this point of time. So, what's the solution? The solution should ideally be offered by the digital synthesizer you're using. During the design of these synthesizers, or effect units, aliasing should be accounted for and avoided in the first place. In Audacity, if you go over to Generate and Tone, you can find that Audacity offers Square, no alias, as a waveform type. We'll plug the same frequency to Generate. Sounds promising. Doesn't seem like there's any aliasing. You can find that the 8 partials that are meant to be in the signal are the only 8 that are present when aliasing is taken out of the picture. This was achieved by limiting our frequency content when generating our square wave, and Audacity probably used additive synthesis to choose only partials below the Nyquist when generating the square wave. But what do you do when your synthesizer offers no defense against aliasing distortion? There are ways to overcome most of the aliasing distortion. We can use oversampling and downsampling. Open a new project in Audacity and select the project rate as 192 kHz. That's a little more than 4 times as high as 44.1 kHz. We'll generate a regular square wave that we know will contain aliasing distortion and click OK. Well, that's not bad. It still contains a bit of inharmonic roughness that's caused due to aliasing, but it's nowhere near bad enough when compared to the signal generated when the project rate was set to 44.1 kHz. If we look at the spectrum, we can understand why this is the case. All we did by sampling higher is we moved the bar beyond which folding occurs from 22.05 kHz all the way up to 96 kHz. All of these frequency components here are in the signal, but they're above the audible limit, so we can't hear them at all. The only ones we can hear are the frequency components that were folded back at 96 kHz and traversed back all the way down to the audible range. However, the intensity of all these aliased components that are audible are considerably low, and that's the reason you hear less aliasing distortion. At this point, the signal can be resampled down to an appropriate sample rate. We'll select the track, go to Tracks, and resample, and we'll set it to 44.1 kHz. Audibly, we didn't change any aspect of the signal when we resampled down. Audacity used the appropriate anti-aliasing filter to remove these frequencies that we weren't able to hear anyway. Internally, this is how a lot of plugins and digital synthesizers work. They oversample and then downsample to get rid of aliasing. We used a rough factor of 4 when oversampling from 44.1 kHz to 192 kHz. Digital softwares are known to oversample from a factor of 2 to even 16 or 32 sometimes. Performing this task manually is not ideal at all. And if your software doesn't offer a defense against aliasing, it's time you looked elsewhere. I feel like I want to continue the discussion further and talk about oversampling and decimation in hardware audio interfaces. But I think it can wait, since there are a lot of technicalities of digital audio that we haven't even touched upon. So in the next video, we'll take an in-depth look at bit depth and quantization. We'll look at exactly how our sampled data points are represented in resolution and in format.